Okay, so fluid dynamics part 2, where we talk about buoyancy and density. So the big question is sort of why does something float, and mathematically speaking, how does something float, or when would something float? So first we talk about density, and I know you've heard this expression in chemistry. Measure of mass per volume. So we could think about something like styrofoam as having a very low density, or air, and lead or some kind of metal as having a high density, meaning it's just heavy based on how much of it there is. So density you've heard. In chemistry you probably used centimeters, but no, grams per cubic centimeter is what I meant to say. And then in physics, we're using, instead of grams, we're using kilograms, and instead of centimeters, we're using meters cubed. So this changes things a little bit, but it's still a measure of mass per volume. The variable we use is the Greek letter rho, as in row your boat, although it's spelled R-H, that's an R-H-O, rho, for density. So know that when you see that, we're talking about density, and we're going to measure in kilograms per meter cubed. So let's talk about the density of water here, because that's going to factor into our buoyancy calculations. You may have remembered from chemistry that water has a density of 1 gram per centimeter cubed, or 1 gram per milliliter, and so that makes it really convenient that 1 is a nice number to multiply or divide by. So if we talk about converting that to kilograms per meter cubed, we would say 1,000 grams is 1 kilogram, and we would say what's the conversion between meters cubed and centimeters cubed? So you might be thinking 100, but that's not right. If we look at, picture this right here as a meter stick. Meter stick, meter stick, meter stick. Right, we have 100, and we have 100, and we have 100. 100 times 100 times 100 is actually a million. So there's a million little centimeter, cubic centimeters, like a sugar cube, in this big box that's a meter stick by a meter stick by a meter stick. So if we multiply that out, we basically get that the density of water is 1,000 kilograms per meter cubed. Water's heavy stuff. Okay, let's see if that cleans up here. So this is the one that takes some more thinking power. All right, the buoyant force. So when we look at this guy, rubber ducky, all right, rubber ducky is floating because why? And some answers are, well, rubber ducky's filled with air, and that's related to the answer. Rubber ducky's not that heavy. Rubber ducky has a low density. All right, good. We're getting somewhere. So rubber ducky has a downward force, and that is gravity, or mg. And because rubber ducky is not moving, rubber ducky has an upward force, and we're going to call that the buoyant force, maybe F sub b. And the buoyant force is equal to, you see how when rubber ducky sits in the water, rubber ducky pushes that much water out of the way? So that much water has actually been lifted up. And of course it spreads out over the surface, but as rubber ducky sits in the water level rises by some small amount, depending on how big the tub is. So this would be an appropriate time to bring up this. So let's forget about what that says on the bottom. And this is Archimedes. Well, this is a rendition of Archimedes. And so the story goes that this scientist, there was a king, and the king had a crown. And the king, this crown was given to him. And I'm looking for some blank space. All right, there we go. So this crown was given to him, and he was told that this crown was all solid gold. And the king wanted to know if that was the truth, because he was going to kill the person if it wasn't. So that's what kings do. And the only thing he could think of was to cut it open. But he, it was a crown, right? He didn't want to cut it open. So he goes to Archimedes and he says, "Hey, Archimedes, figure out if this is solid gold." And Archimedes is confused, and so one day he lowers himself into, it looks like he's been working out, lowers himself into the bathtub, and as he lowers himself into the bathtub, he notices that the water level rises. And so he shouts "Eureka!" and runs out into the street naked, screaming, "Eureka, I've found it!" Meaning he's found the way to determine if the crown is solid gold. So he was able to submerge the crown in water. So here's a tub of water, and he measured how much the water level increased by, and from that he was able to determine the volume. He could then weigh it, and from that get the density, and he knew the density of gold. So he was able to say whether the crown was real or not. And I don't know how the story ended up, but I'm sure somebody was killed by the king, so that's how it goes. But anyway, there's our Archimedes, and it's a good story. So, where were we? I got carried away with rubber ducky. All right, here we go. So the idea is that this is the bottom line, is that the buoyant force is equal to the weight of water displaced. So this much water weighs as much as the ducky, because the buoyant force is canceling out the weight of the ducky. So the weight of the ducky is equal to the weight of that much water, and that's the key concept to get here. So I'm going to say that once more. The weight of the ducky is equal to the weight of that much water. I wonder if I could write that. I bet I could. Okay, so weight of ducky equals weight of this, and by this we mean this, water. Key concept. If you got that, you can do these buoyancy calculations. So here's that in formula form. The buoyant force is equal to weight of water displaced, and the weight of the water is equal to, so watch this, density. So this is mass per volume. Let's zoom in. This is mass per volume, and we're multiplying that by the volume, and this is the volume of water displaced, volume, and then we're multiplying that by the acceleration due to gravity. So look at this. What's mass times acceleration due to gravity? You know that. Weight equals mass times acceleration due to gravity. So yes, this is an expression for the weight of water displaced. Rho v g. Almost sounds like Roe v. Wade. All right. Density of water. So we talked about that. We already calculated. It's 1,000 kilograms per meter cubed. Heavy stuff. And Archimedes' principle. Eureka! Be cool if they had cell phones back then and we could actually find Archimedes running through the streets naked on YouTube. It is that the Archimedes' principle, we could say the buoyant force equals weight of water displaced or the volume of submerged object, submerged meaning completely below the surface, all of the object is underwater, volume of submerged object equals volume of water displaced. And by displaced, we mean pushed out of the way. So if you have a graduated cylinder or something and you're measuring, it would be the amount that the water level rises. So you might want to write that amount water level rises right here. And then I think we're done with this. In part 3, we're going to do some sample calculations. Alright, oh yeah, this is getting complicated. Alright, but here's our rubber ducky, and thanks for watching.